Chapter 22, 24 problems in physics, working through some problems in Halliday Resnick and Walker, just to kind of give an overview of the whole textbook, really. And I'm not doing every single chapter, just doing some of them, picking one problem. So we're in chapter 22, electric fields. Let me describe the problem, and then we'll talk about the physics. So here's the problem. It's problem number 31. There's a charged rod. It has a length of 8.15 centimeters, and we're looking at this point right here, which is 12 centimeters from that. The charge in there is negative 4.23. Where did they get that number? I don't know where that comes from. Negative 4.23 femtometers, 10 to the negative 15th. And so they ask for what's the linear charge density. That's easy. And then what's the x component electric field right there. That's what we're going to do. Okay, so let me talk about the electric field. I got my two things up. And then I'm going to solve the problem. And then we're going to do it in Python. It's going to be great. Love it. Okay. So electric fields. We already looked at this idea of the Coulomb force. So imagine I have a charge Q1. I have another charge over here, Q2. We said that there is a vector from Q1 to Q2, and that's the vector position, such that the electric force is 1 over 4 pi epsilon naught Q1, Q2 over the magnitude of r squared. But since that's a vector, that's a scalar, 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 I need to multiply by the unit vector r hat. Now, it's possible that we could say, well, what if I put a different charge there instead of Q1? Well, I could just divide by Q2 and then multiply by my new charge, and it'd be the same thing. So we can actually describe the field of influence around a charge with what we call the electric field. So the electric field would just be this force, E, the electric field, is that force divided by the test charge, whatever test charge we put there, is the force per unit charge. It's a way to describe the interaction before the interaction is even there. And when we were in the chapter on gravitation, that's what it's called, I mentioned the gravitational field, G, which is the force per unit mass interacting with some object. And the same thing is true here, right? We have the electric field, which is the force per unit charge. Now, it's kind of useful to draw these fields. So if I have a positive charge, no matter where I put another positive charge, then it's going to push away, right? So we have an electric field due to a point charge that looks like that. And as I get further away, that field decreases like that. If I have a negative charge, well, then the field points towards the negative charge, and it gets smaller as you get further away, like that. And they have this idea of field lines. Not a huge fan of field lines. Field lines are a great way to draw things if you don't have a computer, but now we have computers, so there's no point in doing that. But any point along a field line, a line tangent to the tangent to the field line would be the direction of the vector, and then the strength of the field depends on how close those lines are together, which it's hard to draw, and it can get you in some problems. I'm just telling you. Now, there's one other thing that we need to know, and that's superposition. So if I have two charges, a positive and a negative right there, and I want to find the electric field over here, well, I'll put it a little bit closer. I have this, I'll call that E plus, is the electric field due to that charge, and then I have this, E minus, the electric field due to that charge. And then the net electric field is just the vector sum of those two. And I think that's about all I want to talk about, because I'm going to do this problem. We're going to integrate. And they do integration in here to show you how to find the electric field due to charge distributions, which is exactly what we're going to do. It's going to be great. OK, let's just do it. It's 24 problems, not 24 lectures, right? OK. So I have this rod. I'm going to redraw it right here. I'm going to put it on the x-axis in the negative x direction. And it's a negative charge, but I don't really care about that. And then I have my point over here. I'll call that point P, just like they did. Now, how do I find the electric field due to something that's not a point? Well, I make it a point. That's what I do. So I can break this into little pieces dq. And then I can find the electric field dE due to that one point. And then if that's a small piece, I can write the following. Let's say this is the vector r from my point to my observation location. Then dE is 1 over 4 pi epsilon naught dq over r hat. And so if I just integrate both sides, I'm essentially adding up an infinite number of infinitely tiny things to get the electric field. And that's what we're going to do. OK, so this problem is pretty straightforward in that everything's in the x direction, right? So I know just by inspection, I can see that if I have all these points, all the electric fields will be pointing that way. There's none that way, none that way. So I only have the x component of the electric field. So I can actually write this as Ex, and then that's just in the x direction. Is that OK? OK. So I have some work to do here. Let's say this is the distance a, and let's call this the position x. So the first thing I want to do is to find that value of r. So r is going to be from here to there. Now that's going to be, I'm going to call that a negative x value. So if I say r, the magnitude, is going to be equal to a minus x, right? So then if x is negative, so that, if I'm way over here at negative L, then it'd be a plus L. That'd be the distance between those two. So that makes sense. Oh, this is squared. Oops. So I can put that in up here, and I get 1 over 4 pi epsilon naught dq over a minus x quantity squared. Now, I can't integrate that, right? Because as I move along here, what's changing? Well, my x value is changing. That's a variable. But my integration variable is dq. So I have a problem. I can solve that by saying that this little piece has a length dx. And then if the linear charge density is q over L, that should be dq over dx. So really it's just saying the ratio of the charge to this little piece to its length, dq over dx, is the ratio of charge to the whole thing over its length. But if that's the case, I can solve this for dq, and I get, well, if you do it in terms of lambda, they had it in terms of lambda. I'm just going to do it in terms of q. So I'm going to say dq is equal to q over L dx. So now I get the following. dE x is, I'm going to pull some constants out front, 1 over 4 pi epsilon naught. And then I have, instead of dq, I have q over L dx. But I'm going to put the q over L right there. The integral dx over a minus x quantity squared. And I'm going to be integrating from here, x equals negative L, to here, x equals 0. Now, you may say at this point, hey, that's an integral. That's not my job. That's math job. I'm going to look it up. That's fine. You could do that. But it's not a bad integral. It's not terribly difficult. There's a great chance for us to practice integration. So here you can kind of see that I have a term here. And since I have x on the inside of that term and I have dx up there, I could be able to do a u substitution. I could say u is a minus x, and then du would be negative dx. So dx is negative du. So if I substitute that in, I get all this constant, 1 over 4 pi epsilon naught q over L, the integral of negative du over u squared. Now that I can integrate, right? Because I have u to the negative 2. I can do an antiderivative. So what do I take the derivative to get u, 1 over u squared? And that'd be 1 over u. 1 over u, the derivative of that's 1 over u squared. But then I have to have a negative sign. Oh, wait. I have to, yeah. Negative. Yeah. So I get this is going to be equal to a negative, and that negative is going to go away over here. And I get 1 over 4 pi epsilon naught. I'm not sure if I should go from negative L to 0 or 0 to negative L. Or does it even matter? I think I should go from, I think I should go from 0 to L, negative L. Okay, so then I get 1 over 4 pi epsilon naught, Q over L, 1 over U, but I can put back in for U, which is 1 over A minus X from 0 to negative L. And that's going to be E. So EX is going to be 1 over 4 pi epsilon naught Q over L. And then I'm going to put this in 1 over A minus negative L, so plus L, minus 1 over A. I think that's right. Now, in order to really understand if that's a good solution or not, we need to reduce that so we can check it. So let's get a common denominator here. EX 1 over 4 pi epsilon naught Q over L. So right here, I'm going to multiply top and bottom by A. So I get A. And that's what I'm going to multiply by A plus L. So I get negative A minus L. All of that over A times A plus L. Okay, now I see I should have gone from X equals negative L to L because up here I get a negative number, and I don't want that. Yeah, we'll just change that. We'll just change it. Okay. So EX is going to be equal to 1 over 4 pi epsilon naught Q over L. A minus A is 0, so I get L over A times A plus L. Those L's cancel. I get 1 over 4 pi epsilon naught Q over A times A plus L. Now, we can check our answer, right? Because we know some things about our answer. I know that a point charge has a value like this, 1 over 4 pi epsilon naught Q over R squared. And so the units for that and the units for this have to match. So that has a 1 over 4 pi epsilon naught, 1 over 4 pi epsilon naught, Q, Q. And then I have distance squared, and right there, that's A. It's an A. That's A meters times meters, so it's distance squared. So that's good. The other thing I can look at is, as I get further away from this thing, it should look like a point charge. That's one of the questions in the problem, right? It should look like a point charge, meaning it should look like that. So if A is much bigger than L, then A plus L is just A, and I get Q over A squared, so that's the same thing. So that's a check too. And then finally, as I get really far away, it should go to 0, which of course it does if it looks like a point charge. Okay, so I made a tiny little error with a minus sign. I'm okay with that. What I'm going to do now is to use this formula and then do it numerically and see if we get the same thing. So numerically in Python, what we're going to do, instead of having an infinite sum of infinitely small things, I'm going to break it into a finite number of pieces, a finite number of point charges, and just calculate the net electric field due to each one of those point charges in Python. Okay, let's do it. Switching to Python, activate now. Okay, so here we are. I am in Python. I'm not going to graph anything. I'm going to put in my constants. K is 9 times 10 to the 9th. Is that big enough for you? It might be better. We had Q. I'm going to use the same value they had up here. I'm not sure why. Negative 4.23. Negative 4.23 times 10 to the negative 15th. L is going to be equal to 8.15, so 0.0815. A is equal to 12, or 0.12. Yep, okay. The next thing I need is in. How many pieces do I want to break this into? Let's just say 5. And I'm going to actually draw the points just so we can see it. You don't have to do that. Now I want to find the charge on each of my spheres, dq, I'm going to call it, it's just going to be q divided by n, right? If I have 5 pieces, each of those pieces has 1/5 the charge. The other thing I need to find is dx. How far do I move to get to the next piece? And that's just going to be L over N. Okay, now I'm going to start at a location. I'm going to call this vector RT for temporary, 0, 0, 0. And I'm just going to draw this here. So let's say while RT dot x is greater than negative L, so I'm going to move in the negative x direction, then what I'm going to do is make a sphere. So the sphere, I'm not giving it a name, I'm just making it. It has a position RT. It has a radius of, let's say, L over 40. I just picked a value. And now I want to move my RT. RT is RT plus vector negative dx 0, 0, because I'm going to move in that way. Let's just see what happens here. Run it. And there's my 5 point charges. Okay, I can do more than 5. I'm just starting off with 5. Let's do this. Let's make those yellow, just so they look different. No, I just did yellow. Color equals color.yellow. And then up here, I'm going to make an observation location just so we can see it. We don't have to do that though. So let's say our observation location RO is going to be the vector A0, 0, and let's put a sphere there. I'm just going to put a sphere. Position is RO. Radius is going to be equal to, let's say, L over 60. Let's just see what that looks like. Do I not even see it? L over 60, you should see it. Position is RO. Radius is L over 60. L over 40, let's do. Position is RO. Sphere. Position is RO. Radius is L over. I don't know why I don't see it. Do you see it? Did I misspell something? I must have. Sphere. Position is RO. Oh, A. No, A is 0.12. Let's just do 4. I don't know why I can't see it. There it is. I think I was zoomed out. Okay. So let's go back to 60. Because I have my thing zoomed in too much. There it is right there. Okay, good. Whew. Now what I can do is I'm going to calculate the electric field due to each piece at that location. So I need to start off with an electric field that I can add to. So 0. Now right here, I'm going to calculate R. R is the vector from my observation, from my charge to my observation location. So that means it's going to be RO minus RT. So that's that same thing. And now I can calculate DE. It's going to be K times DQ times norm R, that's the unit vector R hat, divided by mag R squared. Now I'm going to add that to my value. E is E plus DE. Oh, I should print it. And let's print it. Print E equals E, newtons per coulomb. Run it. And there we go. Now, 5 is not that many. Let's just do 200 points instead, because that makes more sense. So I'm going to change this to 200. And again, we don't have to draw these spheres. There they are. And there's my observation location right there. I could draw a vector to represent the electric field too, but I'm not going to do that. What I want to do is to calculate our theoretical value. I'm going to call this ET and the magnitude. And so it's this equation right behind me. So I have K times Q divided by A times A plus L. Yep. And let's print that and see how it compares. Print, I'm going to call this ET, phone home, equals ET, newtons per coulomb. Let's see what happens. Kind of nervous. Same thing. I mean, one's a vector and one's not, because we already assumed the direction for the other one. But we get pretty much the same thing, pretty much the same thing. So there you go. That's the answer. electric fields. Hope you found that useful, had fun. Another problem next time. Talk to you later. A link to the whole playlist is down below. Link to the codes down below too if you want to play with the code.